Okay, and I have someone joining here. So uh, it's a pleasure to have today Amita Das. And as we just confirmed, she was.
Matt, I think you're muted, or is it?
Oh, no, I'm not muted. Can you hear me?
I can hear you.
So as we just confirmed, she was a participant in the early festivals, and in fact, the very first festival in 2001. And there's been a bit of a gap, so it's nice to have her back. Her history is such: she did her PhD in condensed matter physics at IIT Kanpur. So unlike most of us, she's a real physicist by training. And then she moved for her first position to IPR, and there formed a long association with the late Frederman Kaw. And she moved through the system in IPR up to the rank of dean, and then around 2017 moved to IIT Delhi, where she is now a professor of physics. She's a member of several Indian academies, more than one, and a Bose Fellowship winner, and a winner of an award for achievement by female scientists. In terms of research, she's done a wide variety of things. Self-organization in nonlinear systems seems to be a unifying theme, but the nonlinear systems vary a lot. So these include things like familiar goodies like zonal flows and avalanches in magnetic fusion. She's wrote an interesting paper on the competition between these two. More recently, she's moved more to the world of laser plasma physics, in particular studies of solitons and ultra short pulses and strongly magnetized laser plasma interaction. And she's also interested in basic things like particularly EMHD seems to be a topic she returns to throughout her career. So today she's going to tell us about interaction of laser with magnetized plasma.
Thank you, Professor Dan, for your kind words. And let me share the screen. You can see my screen?
Yes.
Hello?
Yes.
Okay. Yeah, it's fine.
So thank you once again for inviting me to the festival and for your kind words. So I would be talking about the interaction of laser with magnetized plasma, which has been a topic on which I have been working for the past couple of years with my students. And some names appear here: Ayushi, Devshri, Lakshman. Some of them are also present here, and Shrivanta Maiti. So the laser, when it interacts with an unmagnetized plasma, that is when there is no external magnetic field, that has been known for a long time. And there have been many applications where the study of this kind is applicable, like for instance, in inertial confinement fusion, particle acceleration, etc. We often encounter the physics associated with laser and unmagnetized plasmas. The fundamentals of this particular regime on the propagation of laser, its absorption, is well established. And essentially the physics relies on the dynamics of electrons, because the laser frequency is very high. And for intense short pulse lasers, the regime is essentially electron dynamics dominated. And also the unmagnetized plasma response is typically known because you will require a very high magnetic field to magnetize the plasma at the fast frequency of the laser. So let me quickly go through the physics of unmagnetized plasma. As I understand, there are some students also here. It is the plasma enters through the dielectric constant, and ions being heavier, the ion plasma frequency compared to the frequency of the electromagnetic wave is typically ignored, and we get an expression in terms of electron plasma frequency. And the plasma is said to be overdense if the laser frequency is less than the plasma frequency. It is underdense if it is otherwise. And the electromagnetic wave cannot enter the plasma if it is overdense, as the dispersion curve in this case shows a cutoff of electromagnetic waves at the electron plasma frequency. So the electromagnetic frequency has to be greater than omega p squared, so that the laser or electromagnetic radiation can penetrate the plasma. And for a typical laser light, which is of 1 micron wavelength, it is not able to penetrate a plasma if the density is higher than about 10 to the power 22 per cc. So the main fundamental here is that the response is in this particular regime, the ion motions are usually considered to be negligible, and the unmagnetized plasma has been studied. A better way to understand it further is to recall the Maxwell's equation. And if you have a plasma slab and the electromagnetic field is incident on it, then this is the dispersion curve, and you have omega p here. And if frequency is higher, only then there is propagation. Otherwise, this is a stop band for the EM radiation from 0 to omega p. The contribution for plasma comes from the currents that are excited in the plasma medium. And it has a limit because J cannot exceed the number density of the electrons into the charge, and the maximum velocity that it can acquire is the velocity of light. So this term has an upper limit, but this doesn't have an upper limit because you can increase it if the frequency of the laser light is high. So for a given plasma, this has an upper limit, and so this balance cannot occur for very high frequency radiations, and that is why the low frequency waves cannot penetrate a plasma medium, but high frequency waves can penetrate inside. And for a transverse wave where electric field, let's say, is directed here, and if the cross section is typically very large, then or in simulations, if we use the periodic boundary condition in the transverse direction, then this extent is infinite, and electrons, because of the electric field, if it is in the non-relativistic intensity, the laser is of non-relativistic intensity, then the V cross B forces are negligible, and the electric field induces a quiver velocity. So that, and which is the velocity of electrons are more compared to ions. So there is a current which gets generated, but there is no space charge which would get generated in this case. So it is it is only that the permittivity of the plasma comes into picture here. To generate space charge, that also happens. There have to be special considerations. So for an unmagnetized plasma, we cannot have the penetration of low frequency waves. And but if by some instance we can constrain by some way we can constrain the motion of electrons, so that the value of J gets limited, then even the low frequency waves can be permitted to go inside the plasma. And one way to do is to have an applied magnetic field which is strong and which restricts the motion of electrons. So then these are the dispersion curves for the X mode configuration. What do I call as X mode configuration? Supposing X is the direction of propagation, or Y is the direction where the electric field, oscillating electric field of the laser is along the Y direction, and the oscillating laser field, magnetic field is along Z, and the external magnetic field is also along Z direction. Then the dispersion curve looks like this, and you can see that this white regions are all the pass bands where the electromagnetic wave can penetrate the plasma. These shaded regions are the regions where the wave cannot penetrate, and they are known as the stop bands. So this is a pass band, and you can see that very low frequency waves can penetrate the plasma in this particular configuration. Similarly, if the magnetic field is, external magnetic field is along the direction of propagation, that is along X direction, then, and there is a plane polarized electromagnetic radiation, which is incident, then that gets converted to left and right polarized wave inside the plasma, which have different dispersion curves. Here also at low frequency, there is a penetration, and this shaded region denotes the stop bands. So in fact, this particular regime where we want to study the interaction of lasers with magnetized plasma has not been studied so far, and these studies are desirable as well as they are very timely, because the technological advancements in recent years have shown that very high magnetic fields of the order of several kilotesla can now be produced in the laboratory, and they can be of time scales of nanosecond duration. So for a femtosecond laser or a pulse having a picosecond duration, they can be treated as stationary, the constant magnetic fields. And in addition, there is also availability of short pulse, high intensity, low frequency CO2 lasers. So they have wavelengths which are 10 times higher than the conventional lasers, which have 1 micron wavelength. And if these two technological advancement, in fact, put the condition for electron magnetization to be at the value of 14 kilotesla, which is about 10 times higher at the moment compared to what has been achieved in the laboratory. And but it is clear that in recent future, this magnetic field can also be perhaps created. And then there is a possibility of direct laboratory experiments in a regime where you can have the gyro frequency of electrons at this magnetic field would be greater than the laser frequency, and which would be greater than the ion gyro frequency. So essentially in this particular regimes, the electrons would be magnetized, whereas the ions would be unmagnetized. So the motion of electrons would get restricted, and this would be give rise to new physics. And it appears that it would be reachable within experimental reach in near future. So my talk outline essentially is to give a flavor of the studies that we have conducted using PIC simulation. PIC means particle in cell simulations, which are very popular for studying laser plasma interactions. And I would just point out at two observations of interest. I would not go through all the results that we have obtained in recent past. And these two results are that I will show a new mechanism of laser that couples energy to the plasma, and that it couples it directly to ions. And if you have very strong magnetic field, then the plasma medium essentially becomes transparent to electromagnetic waves. So these are the two observations that I plan to present in this talk. And then finally, I'll summarize and provide some conclusions. So let me go to the first point. And the conventional schemes of absorption of laser energy rely mostly, they are mostly done by electrons. For instance, the well-known schemes are resonance absorption, vacuum heating, J cross B heating, etc. I'll just briefly point out what they mean. And in this process, ion heating has been often a secondary process, which is desirable. For instance, in the fast ignition concept of laser fusion, you want to create an ignition spark in a plasma. And for that, the pellet is already overdense for any laser light to penetrate. And the energy of the laser gets absorbed by the electrons. And one hopes that these electrons will transfer the energy to ions, creating an ignition spark. And that can happen only through collisional and or collective interactions. The collisional interactions are very inefficient because if higher the energy of the electrons, the coupling between electron and ion is weaker as the Rutherford collision cross-section decreases with the 3/2 power of the temperature or the energy of the electrons. So using magnetized plasma, we have been able to show a new mechanism where there can be a direct coupling of laser energy to ions. Let me briefly talk about these conventional schemes, and so that I can show that in the simulation schematic or the geometry that I choose, all these conventional scheme of absorptions are ruled out. So for instance, if one talks about resonance absorption, then it takes place in a plasma for which the density of the plasma gradually increases, and laser is, let's say, obliquely incident, and it reflects from a point where the density is smaller than the critical density. Critical density is the density of the plasma where the plasma frequency and the laser frequency are identical. So it reflects at a point where the density is less than the critical density. NC is the critical density, and cos square theta. Theta is the angle, incident angle. And so the laser reflects from here, and this point is known as the cutoff. But there is an evanescent wave, laser wave. So if you have a plane polarized laser and it is p-polarized, so the electric field is in the plane of incidence, then there will be an electric field component normal to the along the density gradient direction, and this electric field will have a evanescent, it will go deeper inside the plasma as an evanescent wave. And if it is, if the critical density layer is sufficiently close, then it can go to that point, and at that point, the frequency of the laser matches with the plasma frequency, and the resonant excitation of electrostatic waves happen. And once the laser energy gets converted to the electrostatic waves, there is significant absorption and at this point, and because the electrostatic waves can get converted into heat readily by either collision, like there are many mechanisms like phase mixing or wave breaking, etc. So once it goes into the electrostatic wave, the laser energy is in fact irreversibly gets transferred to the plasma. The other schemes, so for here, one should note that you need obliquely incident laser, and the electric field should lie in the plane of incidence for the resonance absorption to occur. For the vacuum and J cross B heating, again, you have a plasma, but it has a sharp profile, sharp density profile, let's say. So it's an overdense plasma. And if there's an oblique laser incident here, again, having a p-polarized laser, so you have electric field in this plane of incidence. It will have both EX and EY components. X, let's say, is the this direction. Then when it reflects at the surface of the plasma, which is overdense, there is an electric field component normal to the plasma surface. And within the skin depth, it can extract electrons from the plasma to vacuum region, and the dynamics is such of the electrons that their motion gets chaotic, and there is an absorption of energy by electrons. Same thing happens if the laser energy is relativistic, then it can happen even when there is a normal incidence, because in this case, the V cross B force, B is the magnetic field of the oscillating magnetic field of the laser, and J would be the quiver velocity caused by the electric field. So the V cross B force will act on electrons, and they will pull the electrons out in the vacuum region, and their trajectories will get stochastized, and there will be some absorption. So these are the conventional, typical conventional absorption schemes. So now we consider a case where we are choosing a transverse magnetic field, constant magnetic field, external magnetic field. We apply that to arrest the motion of electrons. And the regime is such that the laser frequency lies between the electron and ion gyro frequencies, so that electrons are magnetized at the laser frequency, but not the ions. And from this inequality, you can see that there is a condition on the applied external magnetic field, which depends on laser frequency. So smaller the frequency of the laser, you will require the magnetic field strength required to satisfy this condition would be smaller. So for CO2 lasers compared to the conventional lasers, this value turns out to be about 10 kilotesla, in fact, 14 kilotesla, around that. And we have achieved in the laboratory about 1.5 kilotesla. So this was our simulation geometry, and we have used both kinds of codes, PIC simulation. We have used both OSIRIS and EPOCH. OSIRIS was developed in UCLA, and I'd like to thank Professor Warren Murray and Professor Jan Joshi, who have made this code accessible to me. And EPOCH is, I think, in United Kingdom, and it's an open source. So we have a plasma slab, and laser pulse is incident on it, and it has an so this is X is the propagation direction, Y is the direction of the laser electric field, and the direction of Z is the direction of laser magnetic field as well as the applied external magnetic field. So this is the configuration that we have used. And this, as you can see, the laser pulse is normally incidence. So it avoids all resonance as well as vacuum heating, etc. And the amplitude of the intensity we have chosen in such a way that it remains in a non-relativistic regime, so that even the J cross B heating will not occur. Now it should be noted that in a magnetized case, now the charged particles will suffer an E cross B drift. So it appears that both, I mean, like electrons will definitely suffer. Now their motion will be governed by the E cross B drift, where B is the external magnetic field and E is the oscillating electric field of the laser pulse. So in the presence of a time-dependent electric field, the expression for E cross B drift gets modified. I mean, usually we are familiar with this term doesn't come. This is the gyro frequency for the species, any species, and this is the laser frequency. So if E is time-dependent with a frequency omega, then this is the modified expression. And the direction of E cross B drift for this particular configuration, if you look at it, E is along Y, B naught is along Z. I mean, E is oscillating along Y, B naught is along Z. So the E cross B drift direction will be along the propagation direction, back and forth. And clearly, now the E cross B drift for ions and electrons will be different, because the gyro frequency of the two cases have different inequalities. So there would be E cross B drift will give rise to a current, effective current. Normally it doesn't, but in this case it will be. And since E also has a, I mean, it is a function of propagation direction. It is a function of Kx, so it depends on X. So this current will have a X dependence, and so its divergence will be finite, and that divergence of J from the continuity equation clearly will give rise to space charge fluctuations. So electrostatic fluctuations, we think would definitely get generated in this particular case. So this is the background, and let's see what happens when we do the simulations. So simulations, we were very conservative and we did 1D simulations initially, and we have taken a reduced mass ratio because we wanted to explore the fundamentals, in fact, and with the limited resources, computational resources we had to play around and be very particular about the parameters and choosing appropriate numbers. So we chose Mi by Me to be about 25 and reduced mass, and the intensity of laser was chosen to be non-relativistic, and these are basically some of the plasma and laser parameters. And let's see what happens. So when we do not have any external magnetic field, then this is the laser pulse, this dashed black line. Here it is vacuum, and on the right hand side, this is an overdense plasma medium. So when the laser hits this surface, it just reflects back. So t equal to 0, it is here, and it gets reflected back if we do not have any external magnetic field. But when we have an external magnetic field, then something, and this is a plot of oscillating magnetic field of the laser, so electromagnetic component. So there's something which penetrates inside the plasma in this particular case. And when we looked at the density perturbations, so when there is no external magnetic field, the plasma surface is pushed identically. Both electrons and ions have identical density. It's only that the surface gets pushed and inside because of the laser pressure. And but if you have an external magnetic field, there is a clear separation between ion and electron density, creating an electrostatic field as expected. So we did, in fact, then we did the two-dimensional simulations also, and we have shown here both the components of electric field. One is EY, which is the oscillating electric field component of the laser, and EX is the electric field, which will be the electrostatic component of laser, electrostatic component, and this will get generated inside the plasma. So when the pulse is outside at t equal to 0, there is no EX, which is denoted by green lines, and this color, background color, denotes the charge density. So brown means at this level it is 0. And at later times, like t equal to 500 and 1000, you can see that inside there is an electromagnetic EY is also there. And in addition, EX amplitude is much higher compared to the EY, as the expanded plots, two of them show here. And they have very clear oscillations. And clearly the electrostatic component is quite high. So what are these frequencies? When we have there's slight when there's no magnetic field, there's slight, only a noise component of electrostatic field, EX. And when we take its FFT in time, it occurs, the peak, very noisy peak comes at the plasma frequency, which one would expect. But when there is a magnetic field present, it happens at a frequency which is closer to the ion related frequency. So frequency spectra shows the importance of ion dynamics in this particular case. And this frequency remains fixed even when we change the laser frequency. So if we reduce the laser frequency, it was chosen to be 0.2 earlier, and if we reduce, this frequency does not change. But the point is that if we go in the stop band, then this disappears, these fluctuations disappear. It's only when we choose the laser frequency somewhere here, which is the pass band. So the laser is, a part of the laser gets penetrated inside the plasma, that you observe these electrostatic oscillation, which is reasonable because after all, the electromagnetic component of E gives rise to the E cross B drift and creates the charge separation. We also, so these are the 2D simulations that we did, and we faced a lot of problem with referees. The major issue was that that the magnetic field of such high magnitude cannot be produced in lab, has not been produced in lab, so it is not, it should not be accepted, and so on. And then because of the 1D nature of the simulation, or because we had, even in 2D simulation, we had chosen a periodic boundary condition. We had not chosen a finite size of the transverse laser pulse. So we did all those studies also, and you can see that we chose a finite transverse extent of the laser to satisfy the referee, and typically nothing changes. And the frequency spectra also remains the same in both the cases. And so finally we could satisfy the referee, and it has been published in NJP and nuclear fusion. And now let me come to the energy absorption. Now, once it is converted to electrostatic fluctuations, basically the laser energy has got irreversibly into plasma, because electrostatic fluctuations will, I mean, the energy would remain in the plasma and they would ultimately get converted to heat or something. So let's look at this figure, which shows all the partitioning of the energy. There are two scales here, and the left and the right scales. The blue curve denotes the laser energy for the two cases, where you have external magnetic field and where it is absent. And the red curve shows the ion energy for the two cases, and the green curve for the electron energy. And these vertical black lines denote certain times, which I'll explain. So this first line is the time at which the laser pulse touches the plasma boundary. Thereafter, a part of it penetrates it and the other part gets reflected. So it is here at this vertical line, the incident laser has totally got reflected, and some portion of it has gone inside the plasma, but it is now traversing through the vacuum region. And at this point, it touches the left boundary of the simulation box. And this drop in the energy is because now it's going outside the box. So whatever remains here in these two curves is the electromagnetic energy which remains in the plasma finally. And you can see that this dotted line indicates the case where there was no magnetic field. So it's very small energy that is retained by the plasma. But the solid line shows there's a significant amount now which has been retained by the plasma. And correspondingly, if you look at the kinetic energy of electrons and ions, for the first case with no magnetic field, the electron energy is higher compared to the second case. So it clearly shows that the electron motion has been arrested. It is no longer free to move, and it has reduced kinetic energy. And the reverse happens for the ions. It is small in the absence of magnetic field, but it is high when the magnetic field when the magnetic field is applied to the system. This can also be seen from the energy counts. So in the first case, when we had no magnetic field, the electron energy is high and the ion hardly acquires any energy at a later time also. And it gets reversed when we apply a magnetic field. Here the ions have higher energy and the electrons have less energy. In the momentum space distribution also, this is pretty evident. When there's no magnetic field, the electrons acquire higher momentum and ions have less. And with time, you can see that ion momenta are, and these denote the energy circles. So ion has acquired a large energy. So now let's ask the question whether we had proposed a mechanism in the beginning that the electrostatic oscillations will get generated because of the difference between the E cross B drift between ions and electrons. Does it indeed happen or not? That should also be checked. So if we look at this expression, when there is no B naught, obviously E cross B drift is 0, and there should not be any charge density separation between electrons and ions. And this is indeed, you can see that blue curve shows the electron density and red is the ion. They follow each other. But as you increase the magnetic field, applied magnetic field, there is differences which start appearing. And so there is a charge separation which occurs. But at very high magnetic field, again, if you look at this expression at a very high magnetic field, uh, this will reduce. I mean, if both the gyro frequency of both the species is greater than the laser frequency, then this will reduce to the original E cross B drift, which is same for both electrons and ions. So there won't be any difference, and there won't be any charge density fluctuation that will get generated. And this indeed can be seen at very high magnetic field. This does not happen. Then we also plotted the energy absorption as well as the total current as a function of BZ, and you can see that a certain intermediate value of B naught is optimum for this process to occur. We also compared the velocities from the simulation and the theoretical value. How do we do that? This is a plot of electron velocities at 2 different times. And what we did is that we this was at as a function of x, you see at t equal to 600. So what we did is that we noted down the electric field, magnetic field is well known. And then we calculated the E cross B drift velocity, which is along Vx, and then plotted the simulation value of E cross B drift also. And you can see that there is a very good match. There is at both the times. And when we did for ions, because ions are unmagnetized, so they just get directly accelerated in this particular regime where for which the laser frequency is in between electron and ion gyro frequencies. You can see that the ions are unmagnetized. So if there is an EX which gets generated, electrostatic field, then it will just get accelerated directly, and there will be a phase difference between the expression force by EAX by m omega, and one indeed sees the phase difference of pi by 2 between the two expressions, and but the magnitude wise there's a good equilibrium. So whatever we had thought about in the beginning, the simulations in fact confirmed that. And these are just the plots showing how electron trajectories are confined, where the ion have a more extended motion in the x direction. This is done by tracking the particles, and we also looked at the time scale of the ion and electron dynamical response, and they occur at the same frequency. So this electrostatic fluctuations, in fact, was classified as the lower hybrid oscillations. So this work, in fact, confirmed that lower hybrid excitation gets generated, and a new absorption scheme, which depends on the E cross B drifts of the two species, was identified, and that leads to the, in fact, the absorption. There's another very interesting observation that we observed, which I had pointed out earlier also, that if we choose the laser frequency in the pass band, then only we get these lower hybrid excitation. If we choose it in the stop band, then obviously the laser is not able to penetrate it. So the excitations are not observed. The lower hybrid excitations are also not observed. But there's something interesting happens. And that is, can be seen by these plots. Here you can see that these are the fluctuations of magnetic field inside the plasma after the laser has left. And at a high time, you observe a very broad disturbance which comes from inside and propagates very nicely ahead of the lower hybrid excitation. And you can clean out these lower hybrid, the electromagnetic part of that by choosing the laser field to be in the region 2, which is the stop band. And you can see that it gets cleaned out, and only this particular very cleaned pulse is obtained at a very later time. And this propagates very stably. And this was structure is identified not only in BZ, but ion density and electron density also. And it is basically, this is a very low frequency oscillation near the magnetosonic perturbations. And if you send 2, it gets excited because of the ponderomotive pressure from the laser pulse, which pushes the plasma surface. And these perturbations happen in both when the laser frequency is both in region 1, in the pass band as well as in the stop band. And the width that gets excited is proportional to the pulse width of the laser. So this essentially we could identify as the magnetosonic perturbation. You can see the scaling of the structure width with the laser width, which is linear. And at very high intensity of laser pulse, it gets converted, in fact, to solitonic pulses. And we could identify them clearly by studying them carefully and using all the width, actually this AL square, which is the amplitude into the width square of the KdV soliton, is reasonably constant, as you can see here. So they get identified as the magnetosonic KdV solitons. And higher the intensity of the laser pulse we choose, the number of solitons that form are more and more. And so basically we have seen that at we have, so far I talked about the first problem that I wanted to show, that where the laser frequency is in between the electron and ion gyro frequencies, but the pulse of the laser, if you look at the frequency of the pulse of the laser, so that, a typical frequency associated with it, that would be even smaller. And that is the ponderomotive force associated with it is also exciting magnetosonic perturbations in the plasma. So now let me come to the second point, and that is that at very high magnetic fields, where even electron and ion gyro frequencies are greater than the laser frequency, plasma becomes, in fact, transparent, and it behaves as if it is in a vacuum. So again, first let me just talk about the X mode configuration. And here we chose a plasma slab, and it had vacuum in both the regions. And so we were wondering if the laser pulse is incident and the applied magnetic field is very large, then how much of it, gets reflected, propagates, gets absorbed, or gets transmitted. And we observed that at very high magnetic field, you can see some of the values, the transmission is very, very high. And as you increase the magnetic field, this becomes very high. The absorption is also less. So there's no electrostatic fluctuation that gets generated. And the reflection is also very small, as the green data shows here. So what is happening? So, and this can be seen from these snapshots also. So I'm comparing the case of where the external magnetic field was 0, totally unmagnetized case. And the second case is where only the electron magnetization is there. And the third case is where both electron and ions are magnetized. So you can see that this merely gets reflected. The entirely, I mean, amplitude, a big amplitude. And if we increase the magnetic field, even this small reflection will not occur. It enters inside and then it comes out as if the plasma is fully transmitted. And this was the X mode configuration. Then we looked at the number density fluctuations for the 3 cases. Case A, as expected, both Ne and Ni are identical. Case B, they are different. In case C also, they are identical. So Ne and Ni do change, but I mean, like they have identical fluctuation. And how do we understand it? Okay, I also did this in the geometry where the B naught was put in the propagation direction. So this I call as a RL mode, because in this particular configuration, left and right circularly polarized light gets generated. So in this case also, so when there is a low value of external magnetic field, that is the electron magnetization only, the E cross B drift will not be along the X direction, but it will be along the Z direction. So that will add to a current. And since there is no, I mean, we are choosing an infinite extent along Z, so that will not give rise to any electrostatic perturbations, but it will modify the plasma dielectric constant. So you will have a different dielectric constant, and that leads to the left and right circularly polarized wave. But if we increase B naught further, so that even ions and electrons both get magnetized, then again, this behaves like transmitted medium. So both in X mode and RL mode, you get this behavior. And let me show some of the movies. One movie where this comparison will be very clear to you. So this is the case where I'm having these blue lines are the plasma boundaries. This is vacuum here, both cases. This has a high magnetic field. Yeah. And this has a low magnetic field. And there is no magnetic field here. And no plasma also. So this is just vacuum. So now let's see what happens. So the laser pulse comes. It strikes the plasma surface. And this is high magnetic field. It doesn't get distorted at all. Here there is a separation between R and L waves. So they get separated in 2 pulses. But note the comparison between vacuum and the plasma. So nothing happens. And exactly the same velocity, same thing. So plasma essentially behaves like a vacuum. And when it hits the other surface also, I've changed the scale. So it comes out from the blue line, exactly like what it did when there was no medium at all. But this one, as you can see, has generated 2 different pulses. So what are our observations? We observe that absorption is negligible, no electrostatic disturbance gets generated, and it's in fact like a vacuum light propagation. And the reasons we see that this happens, one reason is that the stop band shrinks with increasing B, and that is shown in these 2 figures. As you increase the value of B, the stop band of these X or RL modes, they tend to shrink. And so for entire region becomes propagating. In fact, this, if it shrinks very and becomes very small, you cannot choose a frequency in between here, because the pulse width delta omega would be larger than the change that one would have possibly if one wants to have the frequency lie between this region. So the plasma, so this is the stop band shrinks. This is one reason. And the second reason is that there is no absorption because there's no conversion to electrostatic waves. Now, what will generate the electrostatic perturbations? There are only two possibilities of particle motion in the presence of pulsed electromagnetic field and an external B field. The particle drifts are the E cross B drift and the Ponderomotive force. The drift is because of these two. The E cross B drift generates electrostatic perturbation in the X mode geometry, but not in the RL mode. And the Ponderomotive force will generate in both, may generate electrostatic perturbations in both the cases. But let's see what happens to them. It's easy to see that when there are high magnetic fields, I had already explained it earlier, the E cross B drift becomes identical for electrons and ions, so there's no charge separation. There is no current also if we are looking at the RL mode. So the plasma permittivity, which depends on J, there's no J that gets generated. If you look at the expression for Ponderomotive force, for the unmagnetized plasma, there is a difference between electron and ions. There's a dependence on mass. But if we have X mode geometry or RL mode geometry, then these are the expressions. And alpha is 0 for linearly polarized, and these runs were done for linear polarization. Otherwise, it for left, for circularly polarized, it will take plus minus values. And here at large magnetic fields, one can see that the Ponderomotive pressure goes to 0 because this term will dominate and the mass here will get cancelled in this case, and this will happen here also. So there's no Ponderomotive pressure, so it just, the plasma behaves like a vacuum. So this is an interesting regime. And what is essentially happening, that both electrons and ions are moving. They have E cross B drifts, they have, at least they have E cross B drifts. But what is happening, that because it is equal, there's no contribution in J. So it just behaves like a vacuum. And so this is an interesting possibility at high B field where both electrons and ions do respond, but the total current is 0. So EM wave propagates as if it is passing through a vacuum. So let me summarize. So magnetized laser plasma offers interesting possibilities. We have shown that in a very simple geometry, you can excite lower hybrid excitation, and which also gives rise to a novel mechanism of laser energy absorption. We observed at very high magnetic fields, which will be relevant, which can be relevant in some astrophysical phenomena. The plasma behaves as if it is completely vacuum. I didn't talk about the O mode, where the external magnetic field is parallel to the electric field, oscillating electric field of the laser. In this case, one expects that magnetic field will have no role to play. So that is true to some extent, but we have observed interesting features of B field induced harmonic generation. So at the surface, and if the harmonics are, for the harmonic radiation, if the plasma is underdense, then a part of the laser energy indeed penetrates inside the plasma. So there are promising research prospects for future. Ion heating is possible, and one can think of hybrid schemes. So far, in fact, the inertial confinement and magnetic confinement fusion have taken orthogonal directions. They have never been an overlap. But if we think about if we consider magnetized response in laser plasma interaction, one can think of hybrid schemes which uses the best of both the schemes, and smart fusion schemes perhaps can be devised. Some of the related publications are listed here, and I would like to thank you. I end my talk here. Thank you.
All right. Thank you very much, Amita, for stimulating, interesting talk. Questions, ladies and gentlemen?
Should I stop sharing, or should I keep?
Well, usually it's good because people might drive you back to,
Okay.
It's up to you really how you like to do that. I know what you mean. I get tired of staring at a screen. Well, I'll put my own hand up if no one else will.
Okay.
So the chair recognizes the chair. It sounds almost like the Republican Party. But in the magnetosonic soliton, what's the dispersion, right? You normally think of some balance of steepening, which is very easy to understand for magnetosonic waves, and dispersion. What's
Actually, it is a nonlinear regime that gives rise to a soliton. So you have to have the higher order terms, not the linear.
No, but I mean, there must be a soliton as opposed to a shock, right? There shouldn't be a singularity. So something is preventing it from going to singularity. Usually the thing in a soliton is dispersion, right? When you but what is the dispersion process here, or whatever the analog thereof?
Yeah, good question. We actually, now I forget at the moment, we expanded the fluid equations and retained the higher order terms using the reductive perturbator, and then we got the expression. But at the moment I'm forgetting it to specifically answer your question. Yes.
Okay, I had another one before we turned the Legion loose on you. At least I actually had two more, but one for now. You mentioned actually early on with the J cross B heating and all of that, stochasticity and chaos and all that good thing. What's the mechanism for the origin of the chaos, and how does the strength of the chaos, in other words, say the orbit separation time, you would call it the Lyapunov time, how does that scale with the parameters of the problem, like the laser intensity, the E fields and other such things? You see what I mean? What's bringing the stochasticity here?
There's a very nice article by Brunel, and I forget the scaling, but what happens is that since the interface is very sharp, so when the electrons are evaporated from the plasma outside, they encounter and layer wise they are coming out. So they are experiencing an oscillating electric field of the laser, and their own self-consistent electrostatic field, because when they are coming out, there's an electrostatic field, the ions are pulling them back, and there is a charge separation. So the oscillating electric field of the laser, as well as these electrostatic perturbations, they have been able to show using simple, I think, models, that the trajectories become chaotic.
Mm-hmm. All right, so I'll shut up for a while. Guillaume.
Well, I have much more basic questions. As you mentioned, the very high magnetic field. I was wondering whether the natural choice is if you go to astrophysics and you consider, I don't know, pulsars or whatever, do you think that the new absorption schemes on the fact that you would heat differently ions and electrons depending on the B field, the ambient B field, would change what what you would understand of those objects, or did you see any applications there to better understand those objects?
Actually, I can't hear you. Maybe can you speak a little louder?
Ah, okay, sorry. The very high magnetic fields that you
Yes.
mentioned, one can think directly of, well, it's difficult to produce on Earth, but you can think that they exist in astrophysical objects.
Yes.
So I was wondering whether in pulsars or those very high magnetic field objects that lay around, you would have indirect verification of the mechanisms that you put forward, and how would that, on the reverse question, is how those schemes could help better understand some conundrums there.
Yes, very good question. And in fact, we were thinking, but we have to interact with some astrophysics experts to understand how it is, like how it can be done, how they observe and how they can identify. Because I mean, we feel that even if there is a plasma and some radiation is coming, it will just pass through the plasma if there is a strong magnetic field. And in pulsars, they are of the order of megateslas, as I understand. So, but how to observe it, I don't know. I have to, yes, really would have to interact with an astrophysics person.
Okay. Maybe last question. Coming from MFE, you from magnetic fusion, you say in the end that it would be nice to apply those things to heating in magnetic fusion. So the question is, well, you have those interesting things that with the very high fields, B fields, your pulses, the plasma is transparent. So you could think of if you inject on the high field side, it first it's transparent and then it's absorbed in the bulk. But then the question is, how big is the magnetic field that you need to have this kind of behavior? What's the operational window that you would need? Just a curiosity question, I guess.
This is a loud thinking about that, having both the schemes come together. See, the magnetic fusion has its own difficulties. It's a huge device, and the confinement, you use magnetic field to confine it. Whereas on ICF, one has not, I mean, the device size would be very small, and so you do not have to have such big an instrument. But if you use, one of the problems in the fast ignition is that as the electrons, I mean, if you use magnetic field in the ICF device, I see it getting closer to the MCF, the magnetic confinement devices in that sense. And perhaps something in the magnetic confinement can also be thought about, because as I know, the lower hybrid excitation is a very, you have to look at the resonances very, very carefully. I don't know whether this kind of driven excitation, in laser, you have the liberty of having a very high power, but there perhaps at such a big size, maybe the resonance absorption, the resonantly exciting LH would be the only possible way. I do not know. But here, exciting LH is very easy. I mean, it's a driven response of the system.
Okay. Well, thank you very much.
Next customer is Yannick, and then Rick Sidora.
Yes, maybe a question which might look silly, I don't know, but I wonder whether the electron population can be looked at as a fluid population. And in this case, are there situations where the diamagnetic velocity might be of the same order of the E cross B drift?
Diamagnetic drift.
I mean, whether the pressure can be, the pressure gradient can be large enough to...
Perhaps, but these simulations have been done for, at the temperature effects are not here at the moment.
Pardon?
Taken into account. The temperature effects in these simulations have not been taken account.
Okay, okay. But you see...
But the kinetic effects are there because these are PIC simulations.
Mhm. Okay, and from the point of view of the level of the two velocities, are they comparable or?
Level of, you mean typical values I should compare?
Mhm.
I have not done that comparison. Maybe they can be similar.
Okay, thanks.
Okay, now I think we have Rick is now. I saw another hand come and go. So, if you want to ask a question, everybody, please use the raise hand on Zoom. So, but Rick, you never raised your hand, but go ahead.
Okay. Yeah, this question concerns the ions. Nice talk, Amita. Very, very interesting talk. Question concerns the ions. So what happens if you put two ion species? Right now, you just, I think, used a single ion species.
Yes.
Rather weak mass ratio, but
Yes.
I was curious. So two questions. One is, what happens when you introduce a second ion species? Then you can also, get sometimes these ion hybrid
Yes, that
resonances.
would be even interesting because now you have even more different regimes. Like you can have laser frequency between electron and the two ions, and or somewhere. So you have more regimes to explore. That is a very good suggestion. Yes, and they can give to even more richer class of perhaps. Yes, that's indeed.
And I think you, just from your parameters, quick scan of your parameter list, you use the mass ratio, low mass
We
ratio.
also took, we took 25 and then we also repeated it for 100 also.
Okay, so I'm just curious if you did the mass scaling.
We did.
To the limits that you can, I guess.
Because 25 has a very small range. In fact, if you have a vast difference, then having the separation between electron and ion will be even more better.
And the ion collisionless skin depth, C omega pi, is that some kind of characteristic scale of your magnetosonic soliton? Or what sets the scale of the soliton? Is it?
That's what
Yeah,
I asked.
that's correct. That's correct. It
Okay.
is the C. Yes.
Okay.
Yes.
Good. Yep. Thank you.
Thank you.
So let me ask another question. At what point, I mean, you've got a strong magnetic field and high power laser going. At what point in the game do you have to start worrying about radiation reaction and its effect on trajectories? I mean, one can even go like EM and say, in addition to magnetars, how about just studying simple quantum electrodynamics? But before, let's stay classical, right? When does radiation reaction enter the picture, and what does it do?
There's a limit. In fact, what value it is. There's a talk by Gianluca Sari, and he's identified all the limits where the radiation reaction would be effective, and then how the QED effects will. In fact, for the current, I mean, like last year, there was an inauguration of the ELI laser system, which is a 10 petawatt laser system. And in that laser system, it is possible to study the radiation reaction effects, it seems.
I mean, what
And
does...
perhaps in the beam frame, you can even do some of the QED effects can also be studied experimentally. That is what the impression I have.
I think I know in the US, there's a group formed to study QED effects and these astrophysical effects. What will happen is another matter, right? Talk
Is
is
it
cheap.
NIF or somewhere else?
Well, well, of course, in the US, all things are NIF, but it's not officially. It's more of a, a high energy laser working group. I know Alexei Arifiev is one of the perpetrators.
I see.
Let's see. Any further questions from anyone? All right, let's thank Amita again for a very nice talk, stimulating quite a little different from our others. So thank you very much.
Thank you.
Thank you.